Hello, everyone. So last time we looked at Laplace transform again and some properties such as existence of Laplace transform, so the condition that we need for existence of Laplace transform, and also Laplace transform of derivatives. So if I want to summarize what we have done so far, so we looked at definition of Laplace transforms. We saw that if we have a function f of t and we want to take Laplace transform, then we get a function of s, usually denoted with capital F of s, which is defined as integral 0 to infinity e to power minus st f of t dt. And we saw that the Laplace transform f of t exists if what happens if the function f of t is piecewise continuous and is of exponential order. So if it's of exponential order and if it's piecewise continuous, then Laplace transform f of t exists, meaning that this integral will be convergent. And what was the meaning of being of exponential order? It meant that the absolute value f of t is less than equal to m times e to power ct for some constants m and c bigger than 0. So this was the meaning of being of exponential order. And why was Laplace transform useful or important? Because one can always ask, what's the point of taking Laplace transform if we want to transform a function to another function? So what's the point? Originally, we have a function, let's say f of t. After applying Laplace transform, we get a function capital F of s. So what's the point? The point is Laplace transform helps us to eliminate all derivatives. So once all derivatives are eliminated, then we get an algebraic equation, which we can easily solve to solve for capital F of s. And once we have capital F of s, then we can take inverse Laplace transform to get the original function f of t back. So why is Laplace transform useful or important? Because it eliminates all derivatives. And in particular, we saw that Laplace transform of derivative of a function, let's say f of t, can be defined as s f of s minus f of 0. So see in the left-hand side, there is derivative, f prime of t is derivative of f. But after we apply Laplace transform, in the right-hand side, there is no derivative anymore. It's just s f of s minus f of 0. And we had like another equation for Laplace transform of second derivative, and so on. The Laplace transform of higher derivatives calculated or computed before. All right, now today we want to look at a Heaviside function. its Laplace transform, and its applications. So if you remember, we defined Heaviside function before. So we saw that u of t is defined as 0 if t is less than 0, and 1 if t is bigger than or equal to 1. So we also saw that the Laplace transform of u t minus a will be e to power minus as divided by s. And what is u of t minus a? So here u of t minus a is equal to 0 if t is less than a, and 1 if t bigger than or equal to a. So in pre-calculus, you learned that when you talk about f of t minus a, it will be basically shift a units to the right. If a is positive, f of t minus a will be shift a units to the right. So u of t minus a, we also calculated this algebraically before, that it will be 0 if t less than a, 1 if t bigger than or equal to a, and we saw that Laplace transform of this function is e to power minus as over s. Now today we will use this this is called Heaviside function. We will use this Heaviside function to calculate Laplace transform of piecewise functions. So you may ask, why is it important to calculate Laplace transform of piecewise functions? Well, that will be important in engineering, for example, if you receive a signal, if you start receiving a signal after some time, some certain time, then we can write that as a piecewise function. So it can appear in engineering, for example. So we will get there, but for now, let me first calculate. Now let's calculate Laplace transform of, let's say, f of t minus a times u of t minus a. For a function f of t whose Laplace transform exists. So what will be this Laplace transform? Laplace transform f of t minus a times u of t minus a will be equal to integral 0 to infinity f of t minus a e to power minus st, according to the formula that we had, e to power minus st f of t minus a u of t minus a dt. Now u of t minus a is 0 all the way to a. So if the function is 0, then 0 times anything will be 0, integral of 0 will be 0. So I just need to calculate this integral after a, because after a, u of t minus a becomes 1. Look at here, u of t minus a becomes 1 after a. So this will be same as integral a to infinity e to power minus st f of t minus a dt. Now, how can I simplify this? I can write this one as integral a to infinity e to power minus s times t minus a f of t minus a dt times e to power minus sa. So basically here I multiplied by e to power sa times e to power minus sa, which is 1. So I basically multiplied with 1, which is something I'm allowed to do. And why did I do that? Because, this is t minus a, there is t minus a here. I wanted to have t minus a here so that these two match together. And I can call it, for example, t prime or some other letter, or L, whatever you like. We can use a substitution here. So now let's say, for example, L equals t minus a. Then dl will be same as dt. And if t is equal to a, then L will be 0. If t will be infinity, then L will be infinity. And also dl and dt are the same. So, and dl is equal to dt because a is a constant here. So then the integral here will be f of t minus a, u of t minus a. This will be integral 0 to infinity e to power minus sl f of l dl times e to power minus sa. So e to power minus sa, because it's not a function of L, can be taken out, times integral 0 to infinity e to power minus sl f of L dl. And this is Laplace transform of f. Minus sa here, right? That's minus sa was the term that I took it out of the integral. And this one now is a Laplace transform of f. Instead of t, I have L, but it's the same integral. So still Laplace transform of f. So this is e to power minus sa times capital F of s. So what did we show? We showed that we basically found Laplace transform of f of t minus a, u of t minus a in terms of Laplace transform of f. So we showed Laplace transform of f of t minus a, u of t minus a equals e to power minus as times capital F of s, where capital F of s is Laplace transform of f of t. So for example, let's use this formula to calculate Laplace transform of t times u of t minus 1. So this formula here enables us to calculate Laplace transform of a function of the form f of t minus a times u of t minus a. So here, if I had t minus 1 times u of t minus 1, it would match with the function that I had here. And I could have used this formula to calculate the Laplace transform. But the problem here is Laplace t times ut minus 1, not t minus 1 ut minus 1. But I can easily solve that problem. I just need to write t as t minus 1 plus 1. So I will write this function here, t times u of t minus 1 as t minus 1 plus 1 times u of t minus 1. And then this will be Laplace transform of t minus 1 u of t minus 1 plus 1 times ut minus 1, which means plus ut minus 1. And now I can write this one as Laplace transform. Because Laplace transform is linear, that's what we showed last time. Laplace transform is linear. When we say Laplace transform is linear, means Laplace transform of addition of two functions is same as addition of the Laplace transforms. So this can be written as Laplace transform t minus 1 u t minus 1 plus Laplace transform u t minus 1. And now I can use the formula I had here. A is 1. And my function f of t is t here. So I can say that this is e to power minus a is 1. So 1 times s times Laplace transform t. See? Laplace transform f of t minus a u t minus a is e to power minus a s times Laplace transform f, original f. So my f of t here is t. So Laplace transform t minus 1 u t minus 1 is e to power minus s times Laplace transform t. Then this plus Laplace transform ut minus 1, which means plus e to power minus s times Laplace transform 1. Because here, well, here original function f of t is t. Here original function f of t is 1. So this function e to power minus s should be multiplied with Laplace transform 1. Now what is Laplace transform t? Laplace transform t is 1 over s squared. So e to power minus s times 1 over s squared plus e to power minus s times Laplace transform 1, which is 1 over s. So this is e to power minus s times 1 over s squared plus 1 over s. So this is basically Laplace transform t times ut minus 1. Now we can use this formula also to find Laplace transform of piecewise functions. So next, we will use formula star above. So let me call this one formula star. To calculate a Laplace transform of piecewise functions. So in order to do that, what should we do? First, we will write piecewise functions in terms of u of t. Because we know how to calculate Laplace transform u of t or u of t minus a, or a function times u of t minus a. So if we can write a piecewise function in terms of u of t, then we can find Laplace transform of the piecewise function. So first, let's say if our piecewise function is of the form, let's say if f of t is of the form, let's say some function, let's say g of t, let's say 0 if t less than a, g of t if t bigger than equal to a, then this is very easy. I can easily write this in terms of u of t. Well, this is almost same as u of t minus a, because if you remember, u of t minus a is also 0 for t less than a. But for t bigger than a, u of t minus a is 1. But this one is g of t instead of 1. But I can easily solve that. I can just take g of t out. So I can write f of t as g of t times this function, which is 0 if t is less than a, 1 if t bigger than equal to a. So this can be written as g of t times u of t minus a. So we can write f of t in terms of u of t this way if f of t is a piecewise function like this. So we are done in this case. Now next case, if our piecewise function, let's say f of t, is a function of the form, let's say g of t, if t bigger than equal to a, less than b, and 0 otherwise. So how can we write f of t in terms of u of t in this case? Then I can write f of t. Again, g of t, I can take it out of this function, take it out as a common factor. I can write it as g of t times 1 if t bigger than equal to a, less than b, and 0 otherwise. Now, so the problem reduces to writing this one in terms of u of t. How can I write this in terms of u of t? So we need to write this function in terms of u of t. So let's think about u of t minus a. If I write u of t minus a, u of t minus a. What is u of t minus a? U of t minus a is 0 if t less than equal to a, 1 if t bigger than a. Similarly, u of t minus b will be 0 if t, or we said t less than previously, less than a, t bigger than equal to a. Similarly, 0 if t less than b, 1 if t bigger than equal to b. So here I have a, here I have b. So u of t is 0 all the way to here, and then it's 1. And u of t minus a, that's the situation for u of t minus a. And for u of t minus b, it's going to be 0 all the way to here, and then 1. Now I need to use these two functions to derive a function which is 1 between a and b, 0 otherwise. To look at these two functions, I need to do an operation or combine these two functions in a way, or do an operation between them in a way that I derive a function that is 1 between a and b and 0 anywhere else. Well, obviously u of t minus a does not have this property because u of t minus a is 1 between a to b, but even after b is also 1. Similarly, u of t minus b is not the function that I'm looking for. But does anything come to your mind? How can I combine these two to get a function that is 1 between a and b, 0 everywhere else? Well, if I subtract these functions, see, the function above minus the function below. Well, the function above minus the function below, before a, both of them are 0. 0 minus 0 is 0. Between a to b, this is 1, this is 0. 1 minus 0 is 1. After b, this is 1, this is 1. 1 minus 1 is 0. Which was exactly the function that I was looking for. So I can say now u of t minus a minus u of t minus b is equal to 0 if t is less than a, 1 if t bigger than or equal to a, less than b, and 0 if t bigger than bigger than or equal to b, which is same as the function 1 if t is between a and b, 0 otherwise. So we show that this function here can be written as this function here can be written as u of t minus a minus u of t minus b. So substitute back. Then we get f of t equals g of t times u of t minus a minus u of t minus b. So again, remember our job right now is to consider different types of piecewise functions and write them in terms of u of t. After we do this, then we can apply Laplace transform because we already know how to calculate Laplace transform of u of t. So right now we said that if we have a function f of t, which is of this form, let's say g of t for t between a and b and 0 otherwise, we can write it as g of t times this function, which is 1 between a and b and 0 otherwise. And this function can be written as u of t minus a minus u of t minus b. So if I substitute here, then I'll get f of t equals g of t times u of t minus a minus u of t minus b. Now, if you use a similar idea, you can write a piecewise function where right now our piecewise function had two pieces between a and b, one formula, otherwise another formula, which was 0. Now, let's say if it has more than two pieces, still you can use a similar idea that we did here to write it in terms of u of t. So let me give you an exercise. let's say this time we have 4 numbers. Let's say a less than b less than c less than d. So, and let's say f of t equals g of t for, let's say, t between a and b, and let's say h of t if t is between, let's say, c and d, 0 otherwise, write f of t in terms of u of t. So let me give you a hint here. See, we already know how to deal with our function if it has 2 pieces, let's say t between a and b and 0 otherwise. Let's say if we didn't have this second branch, we know how to deal with it. Well, we can break down this f of t into 2 functions of the form that we considered above. I can write f of t as addition of 2 functions of the form we considered above. So we can write f of t as, let's say, g of t, addition of these 2 functions, g of t if t between a and b, 0 otherwise, plus, let's say, h of t if t between c and d, 0 otherwise. So you can write f of t as addition of these 2 functions, and you know how to write each of these functions in terms of u of t, and then you can just add them together. So before doing an example, let me give you a remark about why it's important to write piecewise function in terms of u of t, and why it's important to take Laplace transform of piecewise function. In other words, why piecewise functions are important, or why do they appear in this context? So remark here, piecewise functions can naturally appear in practical examples since, for example, in engineering, we may want to consider a situation where we start receiving a signal at some time at t equals t naught. Then such a signal can be modeled as, let's say, f of t equals 0 if t less than t naught, and let's say some function g of t if t bigger than or equal to t naught. But because before t naught we don't have any signal, so we can write it as 0, and we start receiving the signal. Now that signal could be anything. That's a separate issue, that how we can model a signal, but, and of course depends on the signal itself, but let's say in general I can call it g of t, which I start receiving it after t naught. So after t naught, my function is not 0 and it's a function of the form g of t. But before t naught, I don't have any signal. I haven't received any signal. So I can write my function as 0. So these functions that we considered above can appear and do appear naturally, in engineering and in physics. And therefore, it's important to be able to solve differential equations, including or in where these functions are involved or included. And in order to solve such differential equations using Laplace transforms, we need to be able to find Laplace transform of functions of this form. So now let's look at an example where we have a differential equation and where a function of this form is appeared in that differential equation, and let's use the Laplace transforms to solve that differential equation. So now we will solve ODEs with including piecewise functions using Laplace transforms. So example, solve the following initial value problem. Let's look at the initial value problem here that we have. So x double prime plus x equals f of t with x of 0 equals x prime of 0 equals 0, and f of t equals 1 if t between 1 to 5 and 0 otherwise. So let's apply Laplace transform to both sides of our equation. So solution, apply Laplace transform to both sides. And what do we get? Then we get Laplace transform x double prime plus Laplace transform x. Because remember, Laplace transform is linear. So Laplace transform x double prime plus x is same as Laplace transform x double prime plus Laplace transform x equals Laplace transform f of t. Remember here, t is the independent variable, x is the function. T is the independent variable. And Laplace transform x double prime, what was it? So it was, recall, let me give you a recall, Laplace transform x double prime. Remember, Laplace transform will eliminate all the derivatives. All the derivatives will be disappeared once you apply Laplace transform. So this will be same as s squared f of s minus sx minus s x of 0 minus x prime of 0 and Laplace transform x prime was s f of s minus x of 0. And here by f of s, by capital F of s, I mean Laplace transform x. And x of 0 and x prime of 0 are both 0 here. So if I substitute them, what do I get? Laplace transform x double prime will be s squared f of s. And Laplace transform x prime will be s f of s. Now, what about Laplace transform of the right-hand side? F of t. Now, for Laplace transform f of t. Now, first, I need to write f of t in terms of u of t. Whenever you want to find Laplace transform of a piecewise function, first, you need to write that piecewise function in terms of u of t. Now, what is f of t here? It's 1 for t between 1 to 5 and 0 otherwise. We already calculated, we already wrote a function of this form in terms of u of t, remember? If we had a function which is 1 between a and b and 0 otherwise, we wrote that function as u of t minus a minus u of t minus b. U of t minus a minus u of t minus b will be the function which is 1 between a and b, 0 everywhere else. Maybe I can call this formula 2 star. So f of t is equal to u of t minus 1 minus u of t minus 5. See formula 2 star above. So Laplace transform f of t will be Laplace transform u of t minus 1 minus Laplace transform u of t minus 5. And we already know the formula for Laplace transform of u of t minus a. We know Laplace transform u of t minus a is e to power minus as over s. So this will be e to power minus s over s minus e to power minus 5s over s. So 1 over s times e to power minus s minus e to power minus 5s. Now this is Laplace transform f of t. We also calculated Laplace transform x double prime and Laplace transform x. So we have everything ready. So let's substitute them back, and then we can solve for capital F of s. Once we calculate capital F of s, we can take inverse Laplace transform to get the original function x of t that we are looking for it. So substitute back. What do we get? We get s squared f of s plus s f of s equals 1 over s times e to the minus s minus e to the minus 5s. So this term is for Laplace transform x double prime plus Laplace transform x, which is this term. Laplace transform of Laplace transform x, we needed it. Laplace transform, because the original equation was x double prime plus x. So we need Laplace transform x double prime plus Laplace transform x. So here, so I don't need Laplace transform x prime because there is no x prime included or involved. So here also I need to have plus f of s, not s, f of s. In the original equation, I have x double prime plus x equals f of t. So when I apply Laplace transform, I get Laplace transform x double prime plus Laplace transform x. Laplace transform x, I called it capital F of s. So this will be replaced by capital F of s. And this will be replaced by s squared f of s, because these two terms are zero, according to my assumption that x of 0 and x prime of 0 are 0. These two terms are 0, and I'll be left with s squared f of s here. So this will be s squared f of s, this will be f of s. And right-hand side, we also calculated it as 1 over s times e to the minus s minus e to the minus 5s. So see now, as we promised earlier, after you apply Laplace transform, all the derivatives will be disappeared, and you can simply solve for capital F of s. Once you solve for capital F of s, which you can easily solve because you have just an algebraic equation, no ODE, just an algebraic equation. Solve for capital F of s, then apply inverse Laplace transform. So then I will have capital F of s times s squared plus 1 equals 1 over s times e to the minus s minus e to the minus 5s. So then f of s will be 1 over s times s squared plus 1 times e to the minus s minus e to the minus 5s. I just divided both sides by s squared plus 1. So x of t, which is what I'm looking for, will be inverse Laplace transform of capital F of s, which is inverse Laplace transform of e to the minus s over s times s squared plus 1 minus e to the minus 5s s times s squared plus 1. Now we know that, well, first of all, inverse Laplace transform is also linear. So inverse Laplace transform of addition of two functions is addition of inverse Laplace transforms. So this one I can write it as inverse Laplace transform of e to the minus s over s times s squared plus 1 minus inverse Laplace transform of e to the minus 5s over s times s squared plus 1. Now, how can I calculate inverse Laplace transform of this function? Well, we know that Laplace transform of f of t minus a, u of t minus a is e to the minus as times Laplace transform f of t. So what does that mean? So that means inverse Laplace transform of e to the minus as times Laplace transform f of t will be u of t minus a times f of t minus a. So this is the formula that we derived above. So if Laplace transform of this function is this function, that means inverse Laplace transform of the function on the right side will be this function on the left side. Because this is the meaning of inverse function. Inverse function changes input with output. So if for original Laplace transform, this is the input and this is the output. For inverse Laplace transform, this becomes the input and this becomes the output. So here I have inverse Laplace transform e to pi minus as, my a is 1 here, times Laplace transform of some function. I need to figure out this is Laplace transform of which function. But once I figure it out, then the answer will be u of t minus 1 for this term, u of t minus 1. Let's say f1 of t minus 1. If I can figure out what f is, or I can call it f1 for the first term, then I need the answer will be u of t minus 1, f1 of t minus 1. So this will be equal to u of t minus 1, f1 of t minus 1, minus, similarly for the second term will be u of t minus 5, my a is 5, well, again, it's the same function, so let me again call it f1, f1 of t minus 5, where Laplace transform f1 of t, I'm assuming is 1 over s times s squared plus 1. So let me explain one more time. Look at this term. Compare it with this. My a is 1. That's obvious. Then I need it's e to the power minus as times some function of s. So it's times Laplace transform of some function, which I don't know yet. But if I look at this term is a term of the form e to the power minus as times Laplace transform of some function, which I don't know yet. I call that function f1 of t. So this function, I wrote it as e to the power minus as times Laplace transform of f1 of t, where my a is 1, and what is f1 of t? f1 of t is the function whose Laplace transform is this expression, 1 over s times s squared plus 1. So once I call this function f1 of t, and I define f1 of t this way, then this formula tells me that inverse Laplace transform of this function is u of t minus a, my a is 1, so u of t minus 1, times f1 of t minus 1. Because I define f1 of t as the function whose Laplace transform is 1 over s times s squared plus 1. Similarly, this one, my a is 5, so u of t minus 5 times f1 of t minus 5. But again, f1 of t is the function whose Laplace transform is 1 over s times s squared plus 1. Because again, in this expression, the expression in terms of s, apart from this e to the power minus as factor, is again 1 over s times s squared plus 1, which is the same as this. And I already defined f1 of t as the function whose Laplace transform is 1 over s times s squared plus 1. So again, the function corresponding to this term, again, will be f1 of t. But this time my a is 5, so f1 of t minus 5. So I know the answer. I just need to find out f1 of t. What is f1 of t? f1 of t is the function whose Laplace transform is 1 over s times s squared plus 1. So what does that mean? So that means f1 of t is inverse Laplace transform of this expression. So lastly, to find f1 of t, note that f1 of t is inverse Laplace transform of 1 over s times s squared plus 1. How do I calculate this? I just need to use partial fractions. So I can write this one as 1 over s minus s over s squared plus 1. Because if I take common denominator, this will be s squared plus 1 minus s squared, which will be 1. So you can write this by guessing. Or you can use partial fraction procedure. Write this one as a over s plus bs plus c. Could write this one as a over s plus bs plus c over s squared plus 1 equals 1 over s times s squared plus 1. And then find a, b, c. So you can either do it this way. If it's hard for you to guess, write this fraction in this form, find a, b, c. Or if you can guess, just write it in this form. Because the common denominator is s over s times s squared plus 1. So it's something over s plus something over s squared plus 1. If I write 1 here and s here, first one will be multiplied with s squared plus 1. And this one will be multiplied with s. So s squared plus 1 minus s squared will be 1. 1 over s times s squared plus 1. So I can just say that check that 1 over s times s squared plus 1 is 1 over s minus s over s squared plus 1. Then I can write this one as inverse Laplace transform of 1 over s minus inverse Laplace transform of s over s squared plus 1. Well, now I can use the table. Use the table. In the table tells me that Laplace transform of 1 is 1 over s. That means inverse Laplace transform 1 over s is 1. Right? See, Laplace transform 1 is 1 over s. So what does that mean? That means inverse Laplace transform 1 over s is 1. Similarly, Laplace transform cos t. The table tells me that Laplace transform cos t is s over s squared plus 1. So that means inverse Laplace transform s over s squared plus 1 is cos t. So 1 minus cos t. 1 minus cos t is the formula for f1 of t. So what will be my final answer? Well, here is my final answer. I just need to replace f1 of t with 1 minus cos t. So I can say that substitute f1 of t back then what do we get? We get x of t equals, what was it? f1 of t minus 1 times ut minus 1. And f1 of t is this. So 1 minus cos t minus 1 ut minus 1 minus f1 of t minus 5 ut minus 5. So it's going to be 1 minus cos t minus 5 ut minus 5. So this is the final answer for our function. The solution of our ODE is this function x of t equals 1 minus cos t minus 1 ut minus 1 minus 1 minus cos t minus 5 ut minus 5. So let me summarize what we did here. We had a differential equation. We wanted to solve it using Laplace transform. We applied Laplace transform to both sides. Then we used the formulas that we had available for Laplace transform of second derivative of a function. On the right-hand side, we needed Laplace transform of a piecewise function. We explained earlier today how to calculate it. So we use those formulas to calculate capital F of S. Once we found capital F of S, the function that we are looking for, x of t, is inverse Laplace transform of that function capital F of S. We applied inverse Laplace transform. Inverse Laplace transform is linear, so it's going to be inverse Laplace transform of first function minus inverse Laplace transform second function. Then we use this formula that again we derived earlier today. Laplace transform f of t minus a ut minus a is e to pi minus as Laplace transform f of t. So that means inverse Laplace transform of right side is left side, because inverse Laplace transform changes input with output. So we got this formula. Now, if we compare this expression here with this expression here, e to power minus as appeared with a1, and this is Laplace transform. The remaining term, which is 1 over s times s squared plus 1, is Laplace transform of some function. I call that function f1 of t. So Laplace transform f1 of t is 1 over s squared plus 1. So I call it f1 of t. So the answer will be u of t minus 1, f1 of t minus 1. Similarly, this one, u of t minus 5, f1 of t minus 5. Lastly, how do we find f1 of t? Well, f1 of t is inverse Laplace transform of this expression. And in order to find it, first we need to write this one using partial fractions. Break it down into this form. And then again, use the linearity of inverse Laplace transform. Write it as inverse Laplace transform first term minus inverse Laplace transform second term. And here we had to use the table. Once we use the table, we can write this one as 1 minus cos t. Substitute back into this equation, and we find x of t. So this is our final answer for x of t, the solution of this initial value problem. Okay, guys.